Well, I'll get started. I think it's time. I will begin with a prayer. So, dear Father, we thank you for this day. Again, I thank you for this class and your creation. Help us to glorify you what we do this day, Lord. Understand a little bit more about magnetic fields, Lord. In your name I pray, Lord Jesus. Amen. So, the time has come for us to begin discussing magnetic fields. And I'm trying to get the top hat up, if you're wondering. Almost got it. Almost got it. Let's see here. Come on. So magnetic fields have, pretty long history, right? We've had the ancients were aware of the magnetic properties of various metals and rocks and things. 8165. So, aspects of electricity and magnetism have been known since, pretty much since there's been people on the Earth. But, of course, we only really came into a complete understanding of it, well, a more complete understanding of it at least, in the early 19th century, right? So that was one of the big things, was the understanding that, in fact, the electric phenomena and the magnetic phenomena are sort of two sides of the same coin, all right? So we've talked a lot about electric phenomena so far, but the rest of the course, largely speaking, concerns magnetic phenomena. And the first thing to know about is an experimentally verified fact, which is that this is the so-called Lorentz force law. And it states the following, that the force is equal to Q V cross B. Now here, B is our symbol for the magnetic field. All right, so B, here's a new player in the game is a magnetic field. So we're going to be studying the properties of magnetic fields over the next, number of class periods. And so I guess I'm taking a somewhat formal approach, I guess you could say. But there is such a thing as a magnetic field, and if there is such a thing as a magnetic field, you can figure out that it's there because in the presence of a magnetic field, if the charge has velocity v, the magnetic force works in this fashion. All right, so like v is the magnetic field. The units for the magnetic field, typical units are T, and T is for Tesla, which is not about a car. It's about a dude named Nikola Tesla. All right, it's got nothing to do with Musk. It's much more recent. But these are the typical units of magnetic field. These are the analog of a Newton, all right? It's sort of like Newton kilogram seconds, Teslas. A more practical unit's probably Gauss. I think 10,000 Gauss is a Tesla. So if you actually had a 1 Tesla magnetic field, that would be stupidly large, all right? Like I think the largest magnetic fields that are possible in experimental settings today are something like 50 Teslas. But hey, I haven't paid attention. Maybe they're to 100. But it takes a lot of finagling and a lot of money, gullible taxpayers, that sort of thing. Anyway, so that's the unit for Tesla. Now, so let me just draw a picture. If we have the velocity looks like this, all right? And let us suppose that the magnetic field, I'll use some red markers to illustrate the magnetic field. I've just always thought of magnetic fields as being red for some reason. I don't know. So if that's V and this is B, where's V cross B? I see some votes for up. Let's find out. Oh, what? So I point my right hand in the direction of V, and I crossed. What did I do to myself? So it's down. Yes, so the Lorentz force here would be, oh no, downward. Right? So what's going to happen is it's going to, the motion, right? So the motion is going to end up getting, what's going to happen? The motion's going to do what? If its velocity is this way, right? It's going like this. What happens past this point? It's going to get bent down, right? Let's take another stock when the velocity, when it's over here, right? The velocity being downward. If the magnetic field is still, just like I said before, out of the board, right? Well, let me write it. So suppose B is out of board. Do we have a symbol for that? I think we do. I think my symbol for that is like this. Right? So just for the reference, into board, what's the symbol for that? Circle with a cross, right? So we have in mind like an arrow. Those are, you're looking at the tail feathers if it's pointing into the board, where it's got like a conical head, it's pointing out at you. I mean, nobody but Rambo uses arrows like that, but whatever. So, so here I do what? V crossed into B, directly that away, right? So the force would be like here, wouldn't it? And then, so what's it doing? It's bending the motion over here like this, right? And if this keeps happening, what's going to happen is you'll go in a circle, right? So one way you could observe the presence of a magnetic field is if you got a charged particle and you observe it goes in a circle, right? Well, the radius of that circle tells you something about the magnetic field that's in play, right? If you knew, like we could figure that out, right? If it goes directly in a circle, right? And the motion is not like relativistic, right? It's slow enough speed, then we can say that QV cross B is what? 1/2 mv squared, right? Because it's circular motion. So the net force, which I'm saying for the sake of the current discussion, is just the Lorentz force. If that was the case, then this would be the formula, right? And, you know, here, if V is perpendicular to B, right, then the angle between them is what? It's 90 degrees, right? So what's V cross B equal to? And I guess to be clear, I'm missing a like minus r hat or something here. The center seeking unit vector. I mean, otherwise I would fuss, right? At no point should you tolerate from me a vector equals scalar equation, because at no point will I tolerate it from you, right? You guys write things like, I don't know, work is a vector. I'll notice that. Yeah. Oh, you did that?
I did that.
Oh, wow. Man. Whew. So no, work, energy is a scalar, right? So scalars and vectors are different. We should not confuse the two. But here, so what I'm saying then, if we look at the magnitude of this equation, right? If we take the length of this side and the length of that side, then that gives me QVB is equal to 1/2 mv squared, right? So if I know the charge, if I know the radius that it's going in, if I know the velocity of the charge, I can figure out what the magnetic field is, right? The magnetic field, the value of it would be, you know, 1/2 mv squared divided by apparently QV, which is what? mv over what, 2q? Right. So let's see here. Let's put some numbers in to gain some sense of it. Like suppose Well, that's weird. Oh my goodness, guys, why you let me do this? Oh man, goodness, guys. I give up. Why would you let me write such a thing and not stop me? 1/2 mv squared. What is that?
Energy?
Yes. Does this make sense?
Oh, it's not a direction.
No. What did I mean to write there? What's that?
Force.
Force, yes. I should have been writing there is mv squared over r, right? Where r is the radius of the circle involved. I'm like, this is weird. It doesn't involve the radius. What's going on? This is an interesting result. Oh, wait a minute. No, it's not interesting. It's just dumb. So mv squared over r is it's centripetal acceleration, right? Yeah. All right. Goodness gracious. You guys failed the test. That was on purpose, of course. Let's see here. mv squared over r. Sure it was. mv squared over r is equal to q of ev is a more reasonable equation to write. Let me erase evidence of the nonsense that I had there before. So, so we can solve for b, and we get what? B is what? mv squared over qvr. And then cancel the v's, and we just get mv over qr, apparently. So let's try putting in some numbers and like think about something that's, you know, relatively oh, what's the word? Plausible physically. So example 1, let's suppose that you observe a charge, the electron, all right? So your charge is the electron, and you observe it has a speed of, oh, let's say 1,000 meters per second, and it is observed to go in a radius of, let's say, 2.0 meters. And, well, we know the mass of the electron, right? So the charge of the electron is 1.602 times 10 to the minus 19th coulombs. What's the mass of the electron? I don't remember, but I can look it up. It is constant number 3 in this lovely calculator. Let's see here. Where's my constant button? Oh, there it is. 0.3. Apparently 9.11 times 10 to the minus 31. Kilograms, right? So what magnetic field would be necessary for this to happen, right? By the derivation we just went through, we would need B is like 9.11 times 10 to the minus 31 kilograms, excuse me, times my speed, which I made up, 1,000 meters per second. All right. And Q, 1.602 times 10 to the minus 19. That's coulombs. And R, which I said was 2.0 meters. That's the magnitude. What would we get? Let's find out. Well, I get 2.843 times 10 to the minus 9 Teslas. Sorry, folks at home. This is the risk you take. Let's see here. So we could also write that as what? Like 2.843 nanoteslas. So we can, one of the things we can extract from this example is also how a Tesla is related to the other units, right? Can you guys tell me? So apparently a Tesla is equal to what? A kilogram, the meters be canceling, right? A kilogram over what? A kilogram over coulomb second. That's one way to look at it. Yeah. All right. So this is like not just a fanciful example. There's actually things called bubble chambers. And bubble chambers, what happens is as like a really high-speed electron rips through this material, it leaves a track of bubbles behind it. And you can actually see like what the radius is of the curvature of its motion when it's going through a given magnetic field. And so from that, if you know the magnetic field, you could do something else, right? You could calculate, well, any number of these things, right? This is a relation between the magnetic field, the velocity, the mass, the charge, and the radius, right? So if you know any collection of these, you can figure out the other one, right? If you see something going in a circular track. Now, what if there's not just a magnetic field? What if there's also an electric field? Well, then the net force, electrically speaking, is what? It's Q times the electric field plus V cross B, right? And if I take the same example I just had, right? If I take the same example I just had and make it into my example, I guess this is example 2. What would the motion be like? Supposing that the magnetic field is out of the board, and let's suppose that the electric field is rightward. What would happen then? So suppose the electric field's like this, constant everywhere, and suppose the magnetic field is, again, out of the board, constant, right? And let's also, again, suppose the same initial condition, namely that the charge is a positive charge. Those are kind of hard to find in nature, but just play with me here. A positive charge Q with a velocity V like so. What's the resulting motion look like? It's not a circle anymore, right? I mean, it would be a circle if it wasn't for the electric field being there, right? But what does the electric field do? It pushes the charge this way, right? So you can use the principle of superposition that says that the net motion is a sum of the responses to all the forces in play. We already know what the response to the magnetic field is. We worked it out over there. So the electric field just makes it drift. So what do you get? I see you guys. So it's like, I tried. But so yeah, you get one of these. If I could manage to get myself to keep drawing a circle perfectly as I was walking at constant speed, then that's what you'd have, right? It's a helix, right? And my picture's not great, but there it is. Any questions before I go on? So this is just the basic concept that we can think about what's the magnetic force on a single charge, right? But what actually is more often important for us to understand in many, many problems, like there exist homework problems about these things, and that's fine. But what's often more interesting to ask you guys about is current, right? So let's talk about current. And magnetic field, right? So suppose you got a wire and you've got a bunch of bunch of positive charges in here, right? And they're moving this way. Then the current, right, is equal to the charge times the velocity, the drift velocity of the charges. All right, so if I've got a bunch of little charges and they're moving along, then if I want to know what, what the current is, it's the, well, I guess I should be more careful here. It's, well, see, if that's the total charge, right? But so here, I guess I need to think about a length, right? So like, if this has length L, let's say, then sorry, I'm lacking symbols here or something. Oh, let me restate this a different way. Rather than, this doesn't really matter too much and it's confusing me at the moment. So let me not get into that. Let me approach this a different perspective. So what is, if that's the length, right? And we have if we have current I flowing this way, okay? Let's look at it that way instead. So I've got a current I flowing this way. The length is L. So my question to you is, how much charge is in the wire? What is current defined to be? It's the charge per time, right? So what happens if I do L times I? What does that give me? Let me just talk about magnitude here for a bit. So the length times I, what is that? Yeah.
Meters per second.
Right. So, I mean, so I agree with you. So length over the delta t, right? Times the charge. So now getting back to that, this is what we would think of as the drift speed. And this is the total charge in the in the wire. Does that make sense? Maybe. If that's the case, what's the magnetic force? So instead of thinking about the whole wire, we can think about like a tiny little line segment, But let's see here. So if I have, sorry guys, magnetic field, forgot my red marker. If we put this in a magnetic field, then every one of those little charges, right? They've got a force, right? And the force on the force is going to be what? All right, so let me just reformulate where I'm going in just a second here. So rather than thinking about the whole wire, let me just think about like a little bit dl, right? Then if I have I times dl, that is dq dt times dl, which I can rewrite as dl dt times dq, right? And that would be v dq, where that's the velocity that the charges are moving. All right, now I'm not making any kind of like, I'm just thinking about a little infinitesimal line segment here. So now, what's the little bit of force on that dq? Well, now we can apply the Lorentz force law on that one little bit of charge that's moving, right? And it would be what? Well, it would be dq times v cross b. All right? Now, this is, of course, the drift speed we're talking about. So we can rewrite that as dq times dl dt. And I need to give this a direction. So I'm just going to call it v hat, if you guys don't mind. V hat cross b. But I'd rather write that as, I'd rather rewrite this, like just instead write it as dl times dq dt. Ah, man, come on. dq dt v hat cross b. Right? Getting to the point, finally. What is dq dt? Well, dq dt times v hat, that's exactly the current vector. So what we're looking at here is I cross b, and I'm going to rewrite this dl over here. So we can do, there's a couple different flavor options you got here, guys. The one way is to do this. df is what I just did. The current vector across the magnetic field dl, right? What's another way we could go? We could write the constant current I at this point times dl cross b. Where L is the vector which points in the same direction as the current. All right, so like, you know, this is parallel to the L vector. The magnitude of the L vector is, you know, in this case, dl. All right, so there it is. Like this is now. So macroscopically, if I is, you know, constant over straight wire, then what do you got? Then the force on such a line segment of wire we could calculate by I L cross B. Or if you prefer, L I cross B. However you want to think about it. So this all involves the cross product. So if you guys are rusty on the cross product, it would be wise to review that, right? I mean, because cross product matters. You need to know the right-hand rule, and you got to, you know, have that all sorted out. Otherwise, none of this stuff will work well for you. So tell me I was, oh man, I feel bad for the people who didn't come today. You know, they missed that bonus quiz before I started taping, you know? Right? Play along. Play along. Let's see here. Oh. All right. Come on. So the bottom line here is that current in the presence of a magnetic field experiences a force, right? This is pretty important because this is the basis on which pretty much all motors work, right? Motors put a current through a loop and they have some kind of magnet, and that magnet is used to make the loop spin as the current flows through it, you know? So you're able to convert electric energy into mechanical energy. So let's take this out for a spin here, see if we can understand it. So example, let's see here. I guess this was example. I'm going to call this isn't really an example. This is more of a derivation. So, example 3. All right, here we go. Let's suppose that we've got a current loop. So I've got a current that's going this way. All right, so current loop. And let's make the magnetic field go into the board this time. What happens? What happens if we put a magnetic field into the board and study the magnetic forces on this current loop? So we're gonna put constant magnetic field everywhere here, all right? And I'm gonna come up with some names for these so that we can keep track of what we're doing, all right? So we're gonna call this L1, right? This over here is gonna be L2. This guy down here is gonna be L3. And over here, we're gonna have L4. And I'm going to call the forces which result from these currents respectively F1, F2, F3, and F4, all right? So let's start with 1. The key thing to use here is what we just derived, which is that the force of the magnetic field on a current is what? It's I, L cross B, right? We're gonna just use that over and over again. So let's try it out. I is going that way. We should say L is going that way. B is going, what did I say? Into the board. So upward, right? So if I'll draw it here. So there's your F1. We get over here to L2. So we do L2 crossed into B. It goes where? I think it's going this way, right? Tell me if I'm wrong. I think L2 crossed into the, yeah. L3. So I put my right hand in the direction of L3. I cross it into the board, down. L4 crossed into the board, that way. And that's what happens. So what's the net force on a loop? 0. This does nothing. How do motors work? Magic, huh? What happens if instead of being directly perpendicular to the magnetic field, right? We have to think about it 3-dimensionally, right? But so example 4, let me try to picture it like this. Oh man, I don't know if I can picture it. Oh, goodness gracious. Yeah. All right, I guess I'll have to draw a picture. Maybe you can make sense of it. So we'll put the current loop like this. All right. Oh man, come on. Son of a gun. All right, and I'll let it go like this way, then that way, then this way, then that way. And we'll make the magnetic field go like this. Everywhere, constantly. If I do that, what happens to the force on the various, I'm going to again number these. Actually, I won't number them. I'm just going to draw it. So, all right, so I go the lower one here. right? Crossed into B. What happens? Maybe it helps if I can picture it more directly. So we've got like, let's see here. So here's the coordinate axes, right? And let's make this be my loop, right? My loop. So then if I do, so the magnetic field's like here, right? So I do current. Okay, for the sake of sorry guys, but I see where this is going. So I can, otherwise I don't know how to do it. So I point my right hand in the direction of the loop, right? And then I crossed into the magnetic field. It's still going, I think, upward, right? And I'm pretty sure this one's also going to be going directly downward, right? How about this one? That way, right? Now it should be, it has to be perpendicular. So the way the cross product works, right, is that it's perpendicular to both of the vectors being crossed, right? So the direction here has to be like, if I were to follow this back like that, it would be like that kind of thing, right? And let's see here, how about this one? So I go like this, crossed into B, and it's like this, right? It's not, my bad, that wasn't correct. It should have been, I'm sorry guys, it shouldn't be along that line, it should be like this. Because it's got to be perpendicular to B and to the vertical, which puts this in like the Y direction, okay? Let me not sell you on the wrong direction. Yeah? So this one also is like that. So what's going on here?
Is the net force
Yeah, the net force is still 0. That's true, because these are still opposite force pairs. But there's torque. That's right. So if you, that's the thing, is there's torque. Now there wasn't any torque here. I don't think, right? There's no twisting there. But here, if I was, for example, to put an axis, if I was to make this the axis, if I was to, say, attach this loop so that it could spin around that axis, what would both of these forces do? If I was to look at it, if I was look at the loop from like top down, you know, like this, then I think this force would be going like this, and that force would be going like that, essentially, right? And so they're doing what? They're trying to make it spin. And this is how motors work, in part. So if your motor's like this to start with, you need to give it a little bit of a, you have to bump it a little bit to get it going, you know? But of course, nothing's ever perfectly like that either, right? Everything's always like a little bit off, so there's always like a little bit of something. But anyway, yeah. So I think that's probably a pretty good place for us to stop today. Next time, I will make this more precise. There's a formula that we can actually calculate the torque due to a current loop. And the other thing we're going to do next time is we're going to actually calculate the force due to a current loop by integrating this. See, we can integrate the force if our wire is like not straight, but it's bent, right? If the wire's in like a loop, then how do you find the force? You have to integrate dF over the wire. So we're going to talk about that. The other thing I would point out before I leave here is that if look at this, see this? Currents, forget about the top. There's more to see from this example if you just look at it, and we'll just say it in words, because we'll do more examples, but I just want to point out while we're at it. If you got a current going up like this, and you've got a current going down like that, right? In the presence of a given magnetic field, what happens? They're pushed apart, aren't they? But if they were going in the same direction in the presence of this magnetic field, I think that they would both be pushed in the same direction. There's something to see there. But anyway, let me not say more than that. I want to give you guys back your test since you're here. So, if you